Well, hello everybody, Dave here, and today we're going to take a look at the chi-square distribution when we actually have a two-way table of data from multiple populations instead of just a one-way table involving one population. It's going to be advantageous to us to understand that instead of doing something like a two-proportion z-test, that we can actually compare all the proportions from different populations simultaneously to achieve some sort of significance result quicker. So let's take a look at a classic example here. We have a restaurant that believes that the background music affects the actual entree that the customers are ordering. And so you can see that we have three types of music. We either have no music, French music, and Italian music in the columns, and then in the rows we have the different entrees that are ordered. We can tell from the raw scores alone that we can see that with French music there was only one Italian entree ordered. So that does suggest that maybe there's a relationship there, but we don't know for sure. We could do a two-prop z-test and compare two proportions again and again and again, or we can use a chi-squared distribution and actually come up with a significance result much quicker. So the first thing we have to do is actually find our conditional distribution. You may recall that from previous studies way back at the beginning of the course, where we take the total of the column and then we find our proportions based upon that column. So for A, with no music playing, there was a total of 84 entrees ordered, and of those you can see 30 were French, 11 were Italian, and 43 were other. And so we've calculated now our conditional distributions for those. With our French accordion music playing, we have our proportions, and with our Italian string music playing, we have our proportions. The key thing to remember here is that you are isolating the variable of no music, and then you are calculating the proportions as a result, hence the conditional distribution. If we took a look at a bar graph of these results, you would see that, again, it's pretty clear that with no music playing, it looks like Italian is ordered less. With French music playing, Italian is ordered way less. But with Italian music playing, Italian entrees are not necessarily ordered more again. And so you see that it doesn't appear to necessarily have a relationship, except for the fact that Italian entrees don't seem to be very popular at this restaurant. But again, we can't just use a gut feeling when it comes to the analysis of this. We need to have some sort of significance test that allows us to discuss these more appropriately. So if we were to write a few sentences comparing the distributions, remember that whenever statistics asks for a comparison to be made, you want to compare them directly. And so there should be some sort of numerical comparison made, not just a simple, well, if you take a look, there's more here, there's less here. The Boolean expressions of greater than, less than, or equal to are always welcomed within a discussion of distributions. Just make sure that you compare them directly. And so if we take a look here, we can see that orders of Italian entrees are very low when French music is playing, but higher when Italian music is playing. It's key to notice here that we have isolated specifically the Italian entrees, and we have quoted values themselves. Don't just say it looks like Italian is not ordered that much, but when it is ordered, it looks like that Italian music is playing more. You got to make sure you show those percentages when you can. Notice that again, we're dealing with French entrees. You want to describe as much as you can, but don't talk yourself out of the right answer. So now that we've done the qualitative analysis, it's time to start getting into the quantitative analysis that involves dealing with the proportions themselves. We don't want to do individual testing. We want to compare all of the proportions simultaneously across these different types of music. And so step one, of course, is to see with an overall test if there is evidence of any differences in these parameters that we're interested in. But more than that, we're going to want to see that is there any specific parameter within this comparison that adds more to the difference or not. And so this is the power of the chi-squared test, is we're going to be able to compare all of these proportions simultaneously and at the same time be able to potentially isolate through follow-up analysis which particular variable added more to the overall conclusion that we make. And so, as we do with all significance testing, we've determined the parameters of interest, and now it's time to state our hypotheses. And with the chi-squared test for homogeneity, homogeneity is a fancy word that means similar or the same. It begins with the following hypotheses. The null hypothesis is there is no difference, that they are homogeneous in nature. The alternate hypothesis, though, is that there is a difference in the distribution of a categorical variable for several populations or treatments. So you'll recall from previous study that based upon our p-value that we're going to get from our chi-squared distribution, we're going to be able to make the conclusion of whether to reject or fail to reject. This particular statement of the hypotheses is a script, so you're going to want to use this in context to the problem. So make sure that this language is used no difference in the null, and there is a difference in the alternate. So you'll recall from the previous lesson that when we have a chi-square distribution, it is dependent upon the degrees of freedom, much like a t-distribution. Well, in this case, because we have a two-way table, we have to calculate the degrees of freedom a little differently. And the first thing we have to do is find the expected values. You'll remember from the previous lesson that the expected count is based upon known proportions. What would the value be given the sample size? And so in this case, the way that we calculate our expected values is going to be taking the total of the column times the total of the row divided by the total of the sampling completely. So if you'll notice at this table here, if we're looking at no music, the total of the column is 84, the total of the row is 99, and the total number of samples taken in this study is 243. So that gives us an expected value of 34.22. Remember that with expected values, we don't want to impose realism in these. These are essentially like an average, which means we can't round this to whole numbers. Make sure you carry it to 2 decimal places, because that's going to help us when we get into our actual chi-squared calculation. So as a summary, the expected count, again, is the row total times the column total divided by the table total. And with these expected counts, we are now ready to determine if the conditions to perform a chi-squared test are satisfied. With random and 10%, that is, as always, the first 2 tests that you're going to want to perform with a proportion scenario. But with the large counts, you'll remember that when we have the expected counts, all expected counts have to be greater than 5. Don't confuse this with the observed counts. Observed counts can be whatever they are, but the expected counts have to be greater than 5. If any one of them is less than 5, then we question the validity of our test. So this looks very similar to the conditions that we did with the chi-squared goodness of fit test. It's just a different way in which we have to calculate a bunch of expected counts with the two-way table. So if I'm doing a question, I strongly encourage you to write out your observed counts table, make sure that you have your totals on that table, and you should list off very clearly the expected counts table to show that you understand that the expected counts are calculated from the column totals and row totals, and that this is a necessary quantity when it comes to calculating the chi-squared. I've given you the equation for chi-squared again. I would encourage you to use technology to calculate it, but at the same time, when you are out to demonstrate an understanding of the topic, you're going to want to show at least a couple of steps of the calculation of the chi-squared. When it comes to the follow-up analysis, actually calculating the chi-squared outright is going to be essential, because you're going to want to see the individual scores of each entry in our observed counts to determine if one of them added more to the chi-squared score than another. And so to calculate the chi-squared now, we're going to take our observed value minus our expected, square that, and divide it by the expected. So I've shown you the case where no music is playing and a French entree was ordered to give you a chi-squared score of 0.52. We know that the complete chi-squared is the sum of all 9 entries, and so you can see that I've just shown you that it is a repetitive calculation to get you a chi-squared of 18.28. Don't be shocked by a chi-squared score being so high. That's pretty standard when it comes to chi-squared. So a chi-squared value of anywhere above 5 to 20 is completely within the range of normal. I would say that this work that I've shown would be the minimum amount of work you'd want to show to make sure that you clearly demonstrate your understanding of the topic. So now that we have our chi-squared score, we are ready to compare this to a chi-squared distribution to get our p-value. But in order to do that, we're going to have to actually determine the degrees of freedom. So again, I want to remind you that we started with the following hypotheses. And in context of the problem, the null would be that there's no difference in the true distributions of entrees ordered at the restaurant with no music, French music, and Italian music. Whereas the alternate is there is a difference. You'll know that the majority of the wording is exactly the same, with the big exception of no difference versus difference. So to find our p-value, we already have our chi-squared score, but we have to determine which distribution we're actually going to get the p-value from. For that, we have to calculate the degrees of freedom. With a two-way table, we're going to calculate the degrees of freedom by taking the number of rows, minus 1, times the number of columns, minus 1. So in our example, we had 3 rows and 3 columns, so our degrees of freedom are 3 minus 1 times 3 minus 1, or 2 times 2, which equals 4. With that, now, if you use a table, you could find out that the p-value is going to lie between 0.001 and 0.0025, a really, really small number. If you use your calculator, there's a chi-squared CDF command that when you do that, you get a value of 0.0011. There is an additional test known as the chi-squared test that exists in TI calculators. Those involve the use of matrices, and if you want to use that, just recognize that there's a little more difficult calculator functions involved that you're going to have to learn before you can use it. So if we're going to interpret the p-value from the calculator, we can see that if there is no difference in the true distribution of entrees ordered, so remember that this was our null hypothesis, then there is a 0.0011 probability of observing a difference in the distributions of entrees ordered. So notice that the first thing we do is assume the null hypothesis is true. And given that, here is the probability that there is a difference. For C, what conclusion would you draw? Well, this is the exact same conclusion you draw with any significance test. If we compare it to an alpha level of 0.05, this p-value is exceptionally small, which means we would reject the null hypothesis. Read what comes next now. We have convincing evidence, that's the language we use, of a difference in the distribution of entrees ordered at this restaurant when no music, French music, or Italian music is played. So that particular statement is what you've been using in all significance testing. So this script that you're going to use is really important. Make sure you put it in context of the problem. Now look at this last statement. Furthermore, the random assignment allows us to say that the difference is caused by the music that's played. So one of the things that we've talked about a lot is, can we determine cause and effect? Well, the only way we can determine cause and effect is if it is done by experimental design, not an observational study. So if random assignment is not performed, then you can't infer a cause and effect. If it is random sampling, you can't infer a cause and effect. So it's important to read into the question and understand that if it's an experiment and there was random assignment, we can infer that the difference is caused by the music that's played. So to summarize the chi-squared test for homogeneity, our hypotheses are going to be that there is no difference versus there is a difference. Then to determine whether the conditions are satisfied, we have to calculate the expected counts given our original data set. Remember that in order to do that, it's the row total times the column total divided by the table total. And then we're going to calculate our chi-squared score, from which, given the degrees of freedom, we are going to determine the p-value and make the appropriate conclusion based upon this p-value. So there's a lot to it, but really the only difference here is the way you calculate the degrees of freedom and the statement of the hypotheses themselves. The follow-up analysis that we can do with this test is very powerful, because not only now have we made a conclusion that there's a difference, we can determine more so which specifically is affected, whether it be strongly or weakly. So you can see that I've given you a table here where we've shown in one column the count, the expected count, and then the chi-squared score based upon those values. And you can see the red box around the Italian entrees when French music is playing and when Italian music is playing. And there is an obvious significant score created by those observations. You'll see that with our total chi-squared score of 18.28, that 7.67 is added to that based upon the one observation of French music playing and you order Italian, and then 6.4 is added to the chi-squared score based upon the Italian music playing and ordering Italian. So this is significant because it shows that Italian entree ordering is greatly affected by Italian and French music. So I strongly encourage you that when you perform a chi-squared test of homogeneity, that not only do you calculate the p-value, but you also show these individual chi-squared scores, and based upon that, do this follow-up analysis where we actually talk about the percentage that is contributed to the overall score based upon a couple of different observations, because that can really lead to further evidence to support more conclusions to be made. So it's a very nice statistical tool to use. There's another scenario we have to consider, and it's if we actually create a two-way table from a single sample, from a single population, but then we're sorting it based upon two different categorical variables. When we do something like this, our ultimate goal is to see if there's an association between the two variables or not, which means with a chi-squared test, we can compare the proportions quickly to determine if there is or isn't an association between these variables. You'll remember that the last time we've done a test like this was way back when we dealt with a scatter plot, where we were trying to see if, given the r and r squared value, if we could make conclusions about the goodness of fit and the strength of association between the two variables. But with the chi-squared test, we can now take multiple proportions and compare them simultaneously. So with the chi-squared test for independence, if we take a look at our tests, again, the randomization condition and the 10% condition are still absolutely important. And with the large counts, as always, the expected counts all have to be greater than 5. Now, you'll notice that there is one small difference between the two tests that's worth mentioning. That when we're dealing with a test for independence, we're going to use data from one sample, but a test for homogeneity uses data from more groups or more samplings. So when you have a two-way table, it's not immediately assumed one chi-squared test or another. You have to read into the scenario to understand where that data came from. So the summary for the chi-squared test of independence is very similar to the test for homogeneity, except for the following. With the hypotheses, instead of no difference in difference, we're going to say there is no association between the two categorical variables, or there is an association between the two categorical variables. Remember, we've done something like this before, but we had quantitative data when we were doing scatter plots to try and determine an association. Now we can determine that with categorical data. If we then go and satisfy the conditions, we're going to calculate our chi-squared value, just like we did in the previous tests. We're going to find the degrees of freedom with the column total times the row total divided by the table total. And from that, we're going to find our p-value. And from that, we're going to make some statistical conclusion. So let's take a look at an example where the type of test we're going to use is not necessarily obvious. We have the case where we're trying to figure out if men and women are equally likely to suffer lingering fears from watching scary movies as children, and the researcher asks a random sample of 117 college students. There's your key statement right there, because we are taking this 117 college students and now we are sorting them according to the categories of male and female, and then we have our answers of yes and no. You'll notice that there's no statement of multiple populations or different variables by which we are then sampling from. This is a single sample that we are now sorting according to categorical variables. So in this case, this is going to be a test for independence. When we go to calculate the chi-squared score, we always have to calculate the expected counts. I would still create a separate table showing the expected counts outright, and then we can see that each individual chi-squared scores that add up to a value of 4.028. We can see that if you are male, look at that score of 1.883. That's a significant value. So perhaps there's something to be said about this particular question. If the question is asked why independence and not homogeneity, go back to the discussion of the data again. It was a single random sample of college students as opposed to random samples from multiple populations. So let's do a significance test. Step 1, we need the hypotheses. Now that we know that it's a test of independence, the null is that there is no association. The alternate is that there is an association, and that's it. It is as simple as that. Put it in context to the problem and leave it with that. So you can tell that with all of these tests, the script that you use for the hypotheses is rather straightforward, unlike the previous tests where the notation can be a little challenging and what values we're doing can be tricky. It's either there is or there isn't. So let's take a look at the individual entries that add up to the total chi-squared score and see if there's anything interesting in there to discuss. Well, we can see again that men who admitted to having lingering fright symptoms account for the largest component of the chi-squared statistic. We had 4.028 as the chi-squared score, and we had 1.883 contributed by the men who admitted to having lingering fright symptoms. Well, that sounds like it's important, and if you take a look at the expected count versus the observed count, you can see that the expected value was somewhere around 11.69, so 11 or 12, and the number of men that actually admitted to it were only 7. So that's significant because we would expect more based upon just our initial calculations. So if we now follow through and actually calculate the p-value and we compare it to an alpha level of 0.01, we can see in the table that our p-value is 0.045, and when we create the script to come up with our conclusion, remember that the first thing we're going to say is if the gender and ongoing fright symptoms really are independent in the population of interest, remember that that was our null hypothesis statement, then there is a 0.045 chance of obtaining a random sample of 117 students, given the chi-squared statistic. Well, that p-value is greater than the alpha level that we're comparing it to, so that would fail to reject the null hypothesis, which means we don't have the convincing evidence we need to suggest that there's an association between the two. Now, if we change our alpha level to 0.05, that is a much sketchier comparison that we have to make because this 0.045 is awfully close to 0.05, and I don't know that I would feel as comfortable saying that that would then reject. So it's important to recognize that in this particular p-values case, we're kind of in a funny gray area where reject and fail to reject are kind of close to each other. That really doesn't convince me that I want to say that there's an association in that case. So folks, it was a long lesson, but we've gone over the 2 different tests that you can perform when we have a 2-way table of categorical variables. And now it's up to you to determine how do I actually identify which test to use, how do I calculate those expected values, how do I calculate the degrees of freedom, and how do I interpret the p-value once I'm there. That sums it up for the chi-squared distribution. Best of luck to you with your practice problems. We'll see you again.